Is this microphone working? Okay. If it's too quiet, let me know, and I can speak louder. Yes, I'm very happy to be here, and I'm really happy that there's so much interest also in this whole field of artificial intelligence. And yeah, today I want to talk a little bit about why I think video games could be the key towards artificial intelligence, and what we do with these computer games to take that next step. And just a little bit. Oh. Now the clicker stopped working. Okay, now it's working. Okay, just a little bit about myself. So I did my PhD. I'm originally from Germany, and I'm learning Danish, but you don't want me to do the talk in Danish, otherwise you wouldn't understand that much. I did my PhD in the States, and then I did a postdoc there as well, and then I started as a assistant professor here at the IT University in 2013, and since 2015 I'm an associate professor there, and co-direct the Robotics Evolution and Art Lab, and I'm also part of the Center for Computer Games Research that does all kinds of research on games. So not just about AI, but also looking at games from a humanities perspective and a lot of different facets. And so my main research is about biologically inspired algorithms such as neural networks, evolutionary algorithms, and I use game as one domain that those can be applied to, and that we can learn from how do those algorithms perform in this domain to use them also later on in other domains. We are also very interested in applying the same algorithms we use for games, for example, to control robots. How many people here know something about like neural networks? Okay, quite a few. Okay. How many people here know something about evolutionary algorithms? Okay. All right. And yeah, today I'm going to talk to you about all these different methods of what you can apply to games and what we can learn from them, and also talk to you a little bit about games that even with the best AI methods, we cannot solve these games yet. So there are a lot of different. So first, one part of the title is artificial intelligence. So what is artificial intelligence? And for those who have been in other parts of this talk, you probably already heard 10 different definitions of artificial intelligence. And the one kind of that I often adopt is creating machines that can do things currently only humans can do. So I think this is a very general, including definition that encompasses a lot of different what people do in AI research. But another definition also is whatever hasn't been solved yet by AI. And so this is what's also called the AI effect, that once like AI can solve a certain problem, then people kind of assume it's not really that complex anymore, so they erase it from that list. So for example, digit recognition. Maybe at some point people thought this is really, you need AI to do this, but now computers, it's really a simple task for computers to do. So maybe we don't think this is AI anymore. The same with chess. If you would have asked somebody maybe 50 years ago if a computer could play chess, that would be the grand goal of artificial intelligence. And now we have computers that your laptop or your phone can beat the grandmaster in chess. So maybe we don't think this is artificial intelligence anymore. So oftentimes when we think about artificial intelligence, maybe we think about those type of tasks. So we often think about controlling kind of robots. Then autonomous driving is certainly one of the things that everybody is currently talking about. Also, healthcare is currently a big thing in how can we combine AI with healthcare. Then face recognition, what you every day when you interact with Facebook, for example, you're actually interacting already with really advanced AI algorithms that detect these faces and label them. And also if you talk to your phone, if you use Siri, that also is based on these deep learning techniques. So there's already, this is what people maybe normally think about AI, like advanced AI methods, but maybe they think less about different types of computer games. So we have all these different types of games here. Does people know what this game is? Doom. Very good. What's this game? Very good. So there's all these different games, for example, StarCraft. Who knows what this game is? Montezuma's Revenge, yes. And we'll talk about this later because, as it turns out, this game is a really complex game for even the most advanced artificial intelligence algorithms. So in this talk, I want to try to convince you a little bit that instead of only dealing with robots and these things, which are also really important tasks, maybe it's also good to looking at these computer games and video games because they can teach us a lot about where we are currently with artificial intelligence and where we need to go to solve more complex problems. So some reasons why I think that games are a good test bed. So games are designed to be challenging for humans, and they're also designed to be learnable. So a game normally you can learn it as a human, you can get better at it. So it's not an artificial domain that somebody came up to test AI methods. It's actually we developed those games to be played by humans, and if humans can play them, then also these artificial intelligence algorithms should play them. So if we make these methods, they are also relevant for us as well. Then we have a lot of different games. We have a lot of different genres. We have driving games. We have open world games like GTA and World of Warcraft. So there's a lot of different complexity that we can use and apply different AI algorithms to. And then the other thing is that we can study those games from different contexts. So we can make AI that plays the game really, really well, but we can also make AIs that play games more like humans. So there are these Turing tests for games where you observe a bot playing a game and then you have to decide is it a human or is it a computer. So there are different challenges that we can use those games for. And then most importantly, they break less often than robots. So if anybody here works on robots, you're probably used to doing a lot of engineering work, and then the robot doesn't work. So that's why I focus most of my work on games, because there are things you can test a lot faster, and once you have something that really works well, then you can apply it on a real robot. But a lot of people that work on research with robots, they're more they spend a lot of time engineering and fixing things that break instead of working on the actual underlying AI algorithms. So in the beginning, there was the board game, and so this is one of the first things that people have applied these AI algorithms to in the context of games. And of course, chess is one of the most prominent examples in that category, and so a lot of research 30 years ago, 20 years ago, was about can we make an artificial intelligence, a specialized intelligence that can solve this game of chess. So the idea was not to make a general intelligence that can do all kinds of things. The idea was to make an AI that can beat the best human in this game that was thought to be if you can solve chess, then you surely have something that has general intelligence. And so I'm going to talk to you a little bit about what different techniques that people use to beat these games, and then go a little bit about the history of where did we go from chess, what other games did we solve, and with what methods did we solve them. And so the basic example of how chess was basically how they were able to beat the best human in chess is based on what's called this tree search. Also, you can imagine it as some kind of planning. So you have the chessboard, and then the computer basically looks at a lot of different possibilities. If you take a specific move from this board, you get to this position, and so only a small subset of the whole board is shown, because otherwise it would be way too big. And then if you would take another position from your current state, you end up in this state. And from this state, then the opponent can take one of these moves, and then it's your turn again. So you're playing this game that you make a move, and then the opponent will make a move, and I make a move again. And so the computer internally can simulate a lot of these different moves through this kind of tree search method and find the best move that it should take in a certain position to maximize its chances of winning and minimize the opponent's chances of playing a good move. So you're playing this is also called minimax, that you're playing this kind of game that I think if I do this, then the opponent can only do this, and when I do that, the opponent can only do this. So you kind of want to you're looking internally to finding the right move to reaching a certain state in the game. And so normally with minimax, you play this game out until the end. So you look at all the different moves, but you can only do this, basically you can't do this for chess because there are too many possibilities. So after already 4 moves in chess, there are 288 billion possible chess positions that you can be in. And chess has more all the potential things you can do in chess are more than the atoms in the universe. So what you have to do, instead of going the tree all the way down till the end and know who won, which you can then use to choose which goal you should do, what people normally did to solve the game of chess is they were designing specific heuristics. So you have a specific heuristic that would, for example, tell you how good is a certain position in chess. How likely are the chances of, if you're in this position, how likely are the chances of winning the game? And so there's a lot of manual, hand-designed heuristics that somehow count the pieces in the board. They look at, like, does the rook have a free row to move in? And they take all those things into account. And then by doing this, we don't have to search for the tree until the end of the game. We can search through a certain state, and then we can ask this heuristic, how good is this position? And then we use this to do the planning algorithm. And so this is a very brief explanation of how this kind of tree search works. But it worked so well that through these techniques, and some clever engineering, some clever heuristics, they were able to, it's almost exactly 20 years ago, I think in May 97, that they were able to beat the first time that an AI was able to beat a human grandmaster Kasparov in chess. Just through these designed heuristics and this kind of minimax algorithm that would cut off certain parts of the tree, so it doesn't have to search through the whole tree, but it only searches a very specific subpart of the tree that likely results in winning the game. And so, maybe we already succeeded 20 years ago in making artificial intelligence. How many people think that? Maybe not that many. Okay. So the question is, now we solved this game of chess that was for a long time one of the grand challenges of artificial intelligence. And now we solved it with this very simple tree search algorithm, planning algorithm. And so it was a very impressive feat at the time, but some things that maybe why we are not quite there yet with artificial intelligence is that it was it depended on very domain-specific heuristics. So a lot of engineering went into designing these heuristics that could tell you how good is a certain state in the game. And if you don't have those, then it would not work. And it was also a very narrow artificial intelligence, which means that it was able to play chess really, really well, like better than maybe anybody here in this room, but it could only play chess. It couldn't tie its shoes. It couldn't translate text. It couldn't recognize letters. It couldn't do anything else. The only thing it could do was playing chess. And so this is what the focus was on for a long time in artificial intelligence, that we would make narrow artificial intelligence that could solve one task really, really well, but if you wanted to learn something else, then it would fail miserably. Another game that has always been the next kind of, after chess, it was the next grand challenge for artificial intelligence, is this game of Go. How many people here know about Go? Okay, almost everybody. So basically Go, the rules are even simpler than in chess. But it has more depth than chess because of the number of potential moves you can do. So basically how this Go works is just that one after the other, you have two players, one puts down a black stone and one a white stone anywhere on this 19 by 19 board, and then you kind of try to surround the enemy. So that's the only rule, that you just put down one stone and then you never move the stone until it's captured by the enemy. So the rules are actually simpler than chess, but the number of moves is like astronomically high that you can do, because you can put the piece anywhere on this board, and then the opponent can put it anywhere on the board. So really quickly, only after a few iterations, you get an explosion of the number of potential moves you can do. So it's impossible to search the whole state space of Go to determine the best move. There has to be some kind of way of, some kind of heuristic, for example. And so one thing that, while we already solved chess 20 years ago, so why didn't we solve Go shortly after that? So the reason is that for Go, it's very, very difficult to design a good heuristic. So in chess, we could say if we have the rock and it has a free row, that's good. If we have more, if black has more pieces than white, that would mean that black would have a higher chance of winning. But in Go, it's very hard. If you look at this board position, how do you design a heuristic if this is a good or a bad position? So that's what makes Go really, really difficult to solve. And one advance that really catapulted the AI of Go, made it a lot stronger, was this what's called Monte Carlo tree search. And Monte Carlo tree search is also, as the name says, is a tree search method. But instead of using a heuristic, what it basically was based on, that you have this tree. So you start with the current game of the current state of the game, and you expand this tree, and at the end you get like this unbalanced tree. But basically, what the important part of Monte Carlo tree search is here, that to determine how good a certain position is, what you just do, you randomly play the game a few times. And you use that random play out. You randomly play the game with random moves. You look at the end. Did you reach a state where you won the game, or did you reach a state where you lost the game? And you use that information to update how good is this position in the tree. And so you think this should never work, like you just play randomly, and then somehow this gives you a good estimate. But if you do this often enough, like thousands of times maybe, then it gives you a good estimate of how good is this position in the game state. And then you can use this to do the planning. And so this idea, it really changed. So when MCTS was kind of introduced in 2006, after like a year, every Go program adopted this MCTS approach. And so really quickly you can see that over the years how far it has risen in the how good are these programs at playing Go. And later on, but still this wasn't enough to beat the best human Go players in the world. So this, which are I think like Dan 9 maybe. And if you would have asked anybody like 3 years ago, how long do you think it would take to solve the game of Go, they would have said it would take another 10 years, because the step from Dan 6 to a grandmaster is like such a huge step that people would have said this would still take another 10 years. And then 2 years ago, DeepMind, Google, they were able to beat the grandmaster in Go. And later on I'm going to tell you, and they still use MCTS, but they combine it with a different technique. And I'll tell you later on how they exactly did that to beat the world champion in this game of Go. But MCTS is still, or Monte Carlo tree search, is still a it's a crucial component of beating a grandmaster. So now I talked a little bit about these board games, but board games are actually only a very small, they're a small subset section of game AI. And so if this is the playing board games well, then it doesn't mean that you can play a lot of other games well. So board games are a small subsection of the large space of potential games that we want our artificial intelligence being able to play. And board games are especially tailored to artificial intelligence because they are oftentimes or most times they are fully observable. So if I show you the game of Go, if I show you a current Go board, this is all the information you need to be able to determine the next move. If I show you a current chessboard, the positions, this is all the information you need to determine the next move. So there's no hidden information in this game. It's not that you have to remember something you did 10 moves ago, because you have it all in the current state of the board. So, and if we wanted to play any game, and then maybe later on more other tasks like robots, we have to deal with this, the issue of things that are not observable, that there's hidden information that we have to deal with. And here's just an example of what else can you apply this MCTS to, this Monte Carlo tree search. So you can not only apply it to these board games, but actually here we apply it to this tree search method to so research that came out from ITU a few years ago, where people applied it to playing Mario. And basically you're searching in the state of where can Mario go next, and based on that you are able to play at superhuman level and able to finish this Mario level. And but of course then we would also actually, when they designed this Mario challenge, so this is a whole benchmark of Mario, they thought it requires more complex AI, so they were actually really surprised as well that this Monte Carlo tree search, or tree search in general, was able to solve this game so well. And there are a lot of other game-based AI benchmarks out there. So Mario is one that has been a lot of interest in the community. People worked on it a long time. But there are other domains out there. For example, there's Civilization. A lot of people now work on Unreal or Doom as a framework for testing the AIs. There is now also StarCraft. So Google DeepMind and Blizzard, they made a collaboration that has where they give you the API to apply this to StarCraft 2. There is arcade learning environment where the goal is to play these old Atari games. Just from raw pixels. And a lot of big companies are now doing research in AI because in game AI, like Facebook is developing this torch graph, DeepMind is doing a lot of this because they also believe that if you can solve any game, if you can learn any game, then that also allows you to learn other tasks as well. And then also OpenAI also has this OpenAI universe, which is this open world. Which is this module that you can plug in, connect to any game. So the games I showed you so far, like the MCTS in Mario, but also in Go or chess, what they all rely on is a model of the world. So you can only do this kind of tree search planning if you know if I do this move, then I end up in this state. If I do this move, I end up in this state. So I need a model of the world that allows me to do this planning. So that's one limitation of the approaches I showed you so far, that they need to have this model that allows you to plan ahead into the future. And if you don't have this model, then it would be very difficult to apply these approaches. And additionally, what I showed you before is that there's a lot of game-specific engineering. So to make this work well in chess, as I said, they have to define these heuristics. To make this work well in Mario, they had to give it the MCTS is certain. They had to prune down the whole complete Mario into the state of the game that they gave the AI to work on. So this was very kind of narrow AI in the sense that it was only supposed to solve a specific task. And now the more recent focus in artificial intelligence in games has been on more this general artificial intelligence. So the idea is having an AI that learns to play, for example, any game without any information that is given to it. And the motivation behind this is that we might not be able to just learn more about AI in general. Like if we have an algorithm that you can just give any game and it learns it, it will give us more information about how to design artificial intelligence. But the other thing is also that if we have these algorithms, they can probably also learn other things. So if you have an algorithm that can learn any game, then maybe if we put it in a robot, it will also work to learn in a robot, or if you put it in some other task, it will also be able to learn this. So this is kind of the motivation, that if we can learn any game, we can also learn a lot of other things from scratch. And so the next step in this kind of AI endeavor have been on learning to play these video games just from raw pixels. And so the idea is that if you can learn a game from raw pixels, then you have one unified interface to the game. So just like we see games with our eyes, the only information that this artificial intelligence gets is the raw pixels of the screen, and then it can control, like a joystick command, what to do next. And the only thing it gets is the screen, and it gets a reward of how good is a certain, did you succeed in the game or did you lose in the game. So if you play a certain game, the only thing that the AI gets is the raw pixels, and it gets the current score if you play a certain game. And the idea is here that if you have a system like this that can just learn from raw pixels, then you can give it a new game. You don't have to design anything around the game. You don't have to make up an interface. You just give it the raw pixels, and it's able to figure out how to learn it. And so this has been the recent focus of a lot of different research labs around the world. How can we make these kind of systems? And here's a simple example. I guess most of you know about neural networks. For those that don't know too much about neural networks, here's a very brief intro. So to solve this problem of learning from raw pixels without any feature engineering, people have resorted to these neural networks which have shown very, very promising in that area. And specifically this field of deep learning that I'm going to talk about in the next slide. And basically, a neural network, so here's a very, very simple neural network shown. And a neural network basically is a collection of these nodes or neurons that are connected to other neurons through these weighted connections. So it's a very simple abstraction of how the brain is wired. And then they send information from the environment. So in this case, for example, this car has rangefinders that determine how far is it from the left and right side of the track. And that information is sent into the neural network. So we have a front, left, right, back rangefinder is multiplied by the weight of this connection. And then we propagate it one layer at a time. And at the output of this network, there are, in this case, 3 neurons that say forward, left, right. And the highest activated neuron is the action we would take in that specific situation. And then basically learning comes down to how do I find the right connections, the connection weights for the car to do the right thing and not crash into the barricades. And so initially those are all random, so the car will do a random behavior. So now I have to see, do I increase the weight of one connection? Do I increase the weight of one connection? And a lot of this recent progress in deep learning has been, in these neural networks, has been on this gradient descent method. So this method has been around for a long time, but now people have found out to make it work really, really well for more complex network. And I'm not going to go into too much detail about exactly how it works, but basically the idea is that you are in a certain space. So each point in here would be a different neural network with different weights. And your current neural network might be here, that you have a certain combination of weights that give it a certain error. So the higher this plane is, the higher is the error, the more the network doesn't do what you want it to do. And basically what you then do is you have to, through mathematical operation, you can determine in what direction do I have to change the weights to decrease the error. And in this case, the error could, for example, be how close does this car drive to a human driver? So I would record a human driver driving in this car, like in the game environment, and then I would check if I'm in the same situation as the human, do I produce the same outputs? And if I'm not producing the same outputs, that gives me some error. And using this error, we can then determine in what direction should I change the weights to make the error, to decrease the error. And this is basically what this deep learning is also based on. And the only difference is that we now have more computational resources. We have larger data sets to make it work really, really well. And the other difference is that we now use more complex networks that basically have a lot more layers in between. Instead of the simple network I showed you before, these networks maybe now have over 100 layers in between the inputs that you give to the network and the outputs you give to the network. And in this case, we've seen an example of a neural network that was able to learn how to recognize different types of images. And what's quite interesting with these networks is that they learn some hierarchical representation of these features. So once these networks are trained, if you then actually look inside, what did they learn is that the first layers learned, for example, to recognize only edges. Then the next layer recognized to certain parts of an object, for example, nose and paw. And then the next part, so the more higher you go up in this hierarchy, the more abstract the kind of features become. And this is also apparently in our brain we find this, that there's this grandmother neuron that only fires when you see your grandmother. And you have something similar here, and it's without that the human designed this, but it just emerges from this kind of training process that you have this hierarchy of different features. But so this was just a quick thing into deep learning, and how does this relate to video games? So 2 years ago, this was kind of how DeepMind, one of the first papers of this company, of Google's company DeepMind, where they got a lot of attention with, is that they were the first to show that they could learn a wide variety of different Atari games just based on the raw pixels of the game, and they could learn some of them better than a human expert. And here you see, and I think nobody 3 years ago would have thought that you can get with this on the cover of Nature with these space invaders, but now DeepMind opened the way for us to do the same thing. What basically you see here is an example of one of these neural networks that the network only gets the raw pixels as input, and then you have these multiple layers that the network goes through, and at the end the network has, 20 different outputs that say, should I move up, down, should I move up while pressing a button, should I move down while pressing a button, and so on. And then initially this is again just random, and then the network might do a certain action that it would actually get a reward. And then what this algorithm does, this deep learning, deep reinforcement learning, is that it changes the weights so that it increases the chances of the network to do the same thing again. So if we found that a certain action led to a reward, then we want to repeat this action. So over time, just by reward, these connections get modified, and after a few thousand iterations, the network is then able to, starting from playing randomly, it's able to play on a competitive human level. And here we have an example of after 10 minutes of training. So this is from this DeepMind paper. Initially, the network is quite bad. So every once in a while, it's able to catch the ball, and this is this breakout game. But it's not human competitive yet. But then if we let it train, so this is after 120 minutes of training, it actually starts to already play like an expert. And then if we let it train even longer, so after 240 minutes, it discovered actually a very, like a trick that only experts apparently use in this breakout, which is quite clever. It tries to make a hole on the left side. And then once it has this hole, it shoots the ball up, and then it doesn't have to do anything anymore. So it's a very clever AI, very lazy as well. But these games, these algorithms have not just been applied to playing Atari games, but they also have been applied to, for example, playing Doom just from raw pixels as well. And you can check out the video as well that I linked there. And one thing that's, I think, most important is that we don't need a specialized AI to play these Atari games. The same AI, basically, that we use for these Atari games, we can then also use for this Doom. So we're moving more towards more general methods that can be applied to a lot of different things, from autonomous driving to playing Doom to playing Atari, and less specialized things, less specialized techniques. But of course, this AI that plays Doom can still not tie its shoelaces as well. And then more recently, so I told you before that they were able to beat also the world champion in Go 2 years ago, what people thought would still be 10 years away. So how did they do that? So this is also based on these deep neural networks, and it's based on this method Monte Carlo tree search. So this is one example that shows that techniques that were around for a while, by combining them in a new way, you can actually get incredible performance boosts. So basically, it's doing the same thing that we did with the Monte Carlo tree search, searching the space of Go boards, of Go states, but it uses a neural network trained on human experts. So on thousands of human experts, we have a deep neural network that would say which are the most promising states to explore, to plan from. So we have a deep network that would say, this is likely where a human would have put the stone. So this is this network here, the policy network, that tells you I'm in the current state, and the human would likely put pieces here and here and here, trained on human experts. And then, and they also had this other network, a value network, that would say how likely are the chances of winning at this particular, from this particular state. And both of these they used to guide the tree search, because there are so many states, to prune down the number of states so that you can search deeper, search more moves ahead. They used a combination of these two networks to reduce the branching factor in this Monte Carlo tree search. And by doing that, and then first learning from human experts, and then further learning just by playing against itself. So it would train for a month just playing against itself, getting better and better. And by doing this, they were actually able to then defeat Lee Sedol, the best Go player in the world, with this computer I think 2 years ago. And so this was a very watershed moment, because they really thought it's going to take a long time to reach this. So what's kind of next on the horizon? Now that Go is pretty much we can't compete with the best Go programs anymore. So now what are humans still good at? How can we still beat a computer when we play against it in a game? And so our last hope right now is, or maybe there are more, but this is one of our last hopes, is this game StarCraft, where you basically, you have these two armies that fight against each other, and you have to collect different resources, and then you have to build buildings, you have to do research. And so there's a lot of different aspects that are involved in this StarCraft. And so here you see an example of it, that you have the computer has to, so instead of Go, this game is a lot more complex, because you don't have a model of the world. The game is not fully observable. You don't know at this point what your opponent is building, and based on what your opponent is building, that might influence what you should be building. And there are a lot more actions that you can do. If Go had a lot of different states, this has even more states. And you can decide to research, you can decide to harvest, you can decide to attack. So a lot of different decisions that the human takes. And so far we are not there yet that we can beat the best humans with our artificial intelligence methods. But we're working on it. And one thing that came out of our lab is where we try to do a similar approach that they have used for AlphaGo, where they started with learning from human replays, so learning from what would a human do in this situation, and apply this to StarCraft. And in this case, we trained actually a deep neural network on what would a human build next. So the only thing we're trying to, the rest that you see is by a hard-coded AI, like the combat and everything else. But what the neural network decides in this case is, I'm in a current state, and the opponent is in a certain state. What should I build next? Should I build an army to attack? Should I build more harvesters? What kind of thing should I build next? And we showed that it's actually possible from a few thousand games of experts in this game. We're able to extract that information to create pretty good AIs that have pretty good openings in, for example, this game of StarCraft. And what you're looking here is actually the AI playing right now and deciding what building should I build next, what troops should I build next. And so this is the neural network that we use for this specific task. And the neural network gets as input the own material that I currently have. Then it gets the material that's currently under construction. It gets the progress of material under construction, and it also gets as input the opponent material. So whatever we know about the opponent is what the neural network gets as input. Because some things we might not know yet, because we haven't seen the opponent yet. But once we know certain things about the opponent, we give it this additional info as into the neural network. And then what the network outputs is actually the probability of what should you build, what unit should you build next. And we were able to show that it's able to learn. So if you see, here's a timeline about the game, and here's what the network says we should build at this specific moment in time. And if you know about StarCraft, and I'm not a good StarCraft player, apparently this is some opening that a lot of humans also use. And we showed that it's able to, the built-in AI that comes with the game, it's able to beat it 68% of the time by capturing the information in these human replays. And so 68% is not, it's good against this AI, but if you let it play against a really good human, it will still lose. So against me it wins, but I'm also not very good at it. So there's still a long way to go to solve this challenge of StarCraft, and we're only looking right now at what to build. But there's also a lot of other open challenges like micromanagement, how should you move your troops around the game, and a lot of different other factors like long-term strategic planning that are very much not solved yet. But we're taking one step at a time with this. So I showed you two different main methods how AI can learn to play different games so far. So one is planning, so tree search methods. The other one is deep reinforcement or deep learning, like where you have a neural network trained to this method, gradient descent method. And the other thing I want to talk to you about that's also been applied very successfully to games is this idea of artificial evolution or evolutionary computation. And that specifically in our research group we work a lot with artificial evolution but also combining artificial evolution with deep learning. And the basic idea behind this artificial evolution or neuroevolution, so neuroevolution is a specific where we're trying to evolve artificial brains to play games or to solve other kind of reinforcement learning tasks. And the basic idea behind this neuroevolution is that we have a population of different DNA that encodes different neural networks. So each one of these encodes a different neural network. And then what we do is we use this to build a neural network, and then we put this neural network, we let it interact with its environment, so it sends certain actions to its environment, like going left, right, and then it gets back from its environment a certain observation, like how far am I from the wall, and then you let this neural network interact with the environment, and then it sends, after it's done, it sends a fitness back, which determines the fitness, the chances of how high are the chances of this DNA to produce offspring in the next generation. So basically, initially we have a population of 100, for example, neural networks that are all randomly connected, and we put them in a certain task, and some of them will perform better than others. Most of them will not do anything good, but one might be able to, collect some reward in a domain, and then this one is able to produce more offspring in the next generation by slightly mutating, changing the connections randomly of this neural network. And if you repeat this process thousands or millions of times, then over time it will get better at its certain task, just through this idea of mutation, crossover, and survival of the fittest. And here's an example of how such an evolved network looks like to play Mario. So Mario we have here, and here on top we have a neural network. And one benefit of evolution is also that it can produce arbitrary neural networks. So this neural network was not designed by a human, but actually determined by the evolutionary algorithm. And here on the left, we see what does the neural network see. So this is the representation of the world that the network sees. So it's not based on pixels, but it's actually based on these boxes. And on the right side, we have the output of the neural network. Like, should it go up, down, left, right? And here we have the neural network itself. And this neural network learned just by initially starting out with a network that has no connections, and then over evolutionary time, by adding connections, by slightly changing these weights, increasing them, decreasing them, it was able to figure out how to play this game quite efficiently. And here we have an example of how these networks look like initially, the initial generation. So we see every time you see this is a different individual from the first generation. So most of them, they just stand in place, don't do anything useful. And then at some point, now it discovered something. that actually just goes right. So the only thing it does is go right. But that's slightly better than just standing around. And then this network is able to go. Here you see the fitness. The fitness is determined of how far it can go. So, and then the next generation would produce more offspring that's like this neural network. So it would maybe add another connection, slightly change it. And then over time, repeating this thousands of times, you get something that's actually quite good at doing this. And so one of the last things I want to talk to you about is, so I'm also really excited about this idea of hybrid intelligence and how it relates to games. And I think this also connects to the talk next week, which is about the citizen scientist that basically tries to do this hybrid intelligence as well. And basically in hybrid intelligence, the idea is that can we, by combining AIs and humans, can we solve tasks that kind of neither one can solve in isolation? And I think especially games are a great way of getting people to participate in this challenge, because games are designed to be fun, so it's easy to get people to play these games and then having them cooperate with an AI in that game to solve things we cannot solve by either one. And so that's one of the as a first step kind of in this quest, we thought, can we, instead of leaving everything to the algorithm to evolve a behavior for Super Mario, can we evolve the humans in the loop? Humans that have no idea of neural networks, they have no idea of maybe how to program an AI for Mario, but can we evolve them in an artificial loop where they breed Mario behaviors instead? So the human is presented with a selection of Super Mario behaviors, which are each controlled by a different neural network. And then the human chooses the one they like, and that's the one that gets a high fitness, and that's the one that gets replicated for the next, that gets more offspring in the next generation. So just by doing this kind of selection process, can we have casual users evolving behaviors in this in Mario? And so we tested this. This is the interface that if you go to that web page that people see, you see a selection of 9 different, they're all controlled by a different brain, and then you click on the one that you like, and then based on your selection, that will create the offspring for the next generation by slightly mutating the brain that you choose in the previous iteration. And by repeating this process, so here we see the number of generations, by repeating this process, starting with random artificial brains, by repeating this process of artificial breeding, we also call it interactive evolution, where you as the human, you decide what's going to survive and what's going to be killed off. By doing this process a few generations, we were actually able to find Mario behaviors that were able to solve Mario levels. And here we have, in the next video, if it would go further. So here we have an example of interesting behaviors that evolved through this process of having a human in the loop, a human deciding what should be allowed to create more offspring. So we have different behaviors like this, I'm going to kill everything that moves Mario, that people were able to evolve, which you can also evolve a peaceful Mario, but this is not what this person decided to do. Here, this one other person decided to evolve something called Catch Me If You Can Mario that just runs along the level without shooting any enemies. So it was based on the personal preferences of what did the users like to evolve. They were able to guide the process, guide the computer, the evolutionary algorithm towards something that played the game like they enjoyed playing the game. And when we asked if it's actually, was it fun to use this, they said it was actually quite entertaining to not play the game, but instead you're the one that breeds these artificial agents. So that can be a game in itself as well. And so the next thing we're looking at now, and we don't have that much results yet, but that we want to apply the same idea to Minecraft. So because Minecraft, for those of you who know, it offers a lot more possibilities maybe than Mario. So can we combine humans with AI in kind of that they can breed any type of behavior in this Minecraft universe. And so Minecraft is also one of the test beds for AI that, for example, Microsoft is working on, because it offers all these different challenges that you can do and like unlimited possibility of different challenges. So now that we have AI that can learn basically a lot of different games from raw pixels, is this general AI? How many people here think this is general artificial intelligence? Okay, one person. All right. Yeah, so I think we're moving a step closer towards a more general AI, but there's definitely a lot of things that they are not good at yet. And so one thing that's important to note, that AIs are very much, that depends very much on the game, what is the AI good at. And it's very much different from like what humans are good at and what the AI might be good at. You would think that Go is maybe a much harder game than playing Montezuma Revenge, which can be played by maybe an 8-year-old. But for a computer, this is actually a lot harder than playing, for example, Go. And so some games the computer is really good at, like pinball or boxing, and then other games like these here, and especially this one, it's not so good at. And the reason is that in these games, you get a reward directly. So you make a mistake, you find out pretty quickly, was it a mistake or not? And similar to games like Breakout, you pretty much know very quickly, do you suck at the game or you played pretty well. But in games like Montezuma Revenge, what you have to do is you first have to collect this, you have to go down, you have to collect this key, then you have to go to a door, open the door, then you have to go to another room, and only then you get feedback from the game that you actually did something useful. So you have to do this whole sequence of different tasks before the game would tell you, was it something good or was it something bad? So you have kind of this delayed reward. And in those games that require this kind of delayed reward, that require this kind of planning, these deep learning algorithms are not very good yet. If we have a model of the world, we can use things like Monte Carlo tree search. But if we just want to learn from raw pixels with a neural network and want to do planning, that's something that's not currently solved yet. And so people got better at this. AIs got better at this game, Montezuma Revenge, as well. But it's very far from how a good human would play this game. And so one other thing that this game, Montezuma Revenge, for example, showed that games with sparse rewards is that people are now also investigating things like intrinsic motivation. So, and I think that's also a very exciting field. So humans play games not just because they want to get a high score, they also play because it's maybe fun to play. They play because you explore different areas. So one thing that people are exploring now, can you add intrinsic motivation to your AI algorithms that play games, which could also be really, really relevant for other things like robotics, where you might not always get a reward, an instant reward as well. So so this intrinsic motivation would be to rewarding it for also exploring different parts of the level or reaching another screen. So you would get extra points for this. And by doing this, that really helped a lot in playing this game, Montezuma Revenge. Another thing where AIs are very much different than humans, these AIs all take thousands or millions of trials to learn a certain game. And if you give this game to a 6-year-old, they will probably figure it out. Maybe they take 10 trials, 50 trials, but they will figure it out before they use 1,000 trials. So these methods are very much still very data inefficient. So and they don't have this kind of common knowledge that we might have. So we see a game, we see a letter in a game, we see something that looks like a skull, so we should probably avoid it. We see a letter that probably leads somewhere, and that's all prior knowledge that the AI doesn't have. It doesn't have this common reasoning. So that's also one area where games can teach us how important is this common knowledge for the AI algorithms to play these games. And now people are also exploring just a study I read yesterday where people changing these games, like, for example, changing how a letter looks like or changing how a skull looks like to see how does that affect humans playing the game. So if I exchange the skull with a butterfly, and you would die by touching it, then maybe it would take you more time to learn it. If I change how the letter works, it would take you more time. So by looking at the differences between how humans play these games and how AIs play the games, we can learn something about what it takes to learn these things from scratch, which should help us in other games. And another thing that humans are still very much better at is you can imagine how you would play the game differently. If for example, this pedal, if I make this pedal slightly smaller or slightly larger, you as the human could adapt. It might take you a few trials, but then you will figure out how to work with this. If I do this with the AI, it will just break. So they did these experiments where they made the pedal bigger, they put the pedal just slightly higher or slightly lower, and then it didn't know what to do anymore, because it learned to match these patterns, but it doesn't have a common understanding of what does this mean to have this pedal, and if it's bigger, I just play slightly different. So that's something that humans are still very good at, whereas AI still need to learn a lot. The other thing is, if you play Super Mario or Pac-Man, I can tell you, now instead of getting the high score, die as quickly as possible. So for you, this would be that's pretty easy. But if I tell this to the AI, you have to retrain it. It's not that it could instantly change a strategy to perform a different type of task. So we as human can also imagine, you could imagine if the ball is 10 times the size, how would you play the game differently? You can imagine this in your mind, but AIs cannot currently, or most AIs can currently not do this kind of imagination of if the rules of the game change slightly, you have to basically relearn from scratch. Another open goal is to have one AI that can play a lot of different games. So currently, I train a neural network on Breakout. Then I train another neural network to play Mario, and I train another neural network to play something else. But the neural network, there's not one neural network that can play all these games at the same time. So when they learn a new game, they almost always forget how to play the game I played before, because they will override the connections in their artificial brains to learn the new task. So that's also a big important challenge. Can you make one AI that can just like we cannot just learn one game, but we can learn a lot of games and we can still remember them. And that's another big important challenge. So it's this kind of general video game playing. And so to wrap up, I think hopefully I was able to kind of convince you a little bit that games are a very good test bed for AI methods, and the research that comes out of this can then also be applied to other tasks as well. So for example, Google, what they learned from AlphaGo, they actually applied to their data centers to reduce cooling by 40%. And if you have Google's warehouse centers and reduce it by 40%, that's, I don't know how much it is, but it's a lot of money that you save. And they were able to do this by using the same approach that they used in AlphaGo. So these insights we learn here, we can actually then apply to other domains in the future. And the games still offer a lot of interesting challenges that are not solved yet. And I think a promising direction to go next is this hybrid intelligence in the game context. And I think another really interesting direction is what's called self-play. And so this is one of the holy grails, basically, of AI, that you, instead of setting up a system and giving rewards, you basically have the AI just playing against itself, getting better and better and better and better and until it's superhuman. And so this is one of the grand challenges, and recently also from DeepMind. They do a lot of interesting stuff. They actually made this AI, they made a new AlphaGo that didn't rely on human experts at all. So it didn't require human replays. And after 21 days, it was able to be the best, just by playing against itself, the best AlphaGo. It was able to beat all the other AlphaGo versions before. After 40 days, AlphaGo surpasses all other versions of AlphaGo and arguably becomes the best Go player in the world. And this was done only by having it play against itself. So it didn't rely any human data. It just played against better and better version of itself in a smart way. And after 3 days, it was already better than one of the older AlphaGo versions. So what I think is also very interesting here, that humans have been playing this game Go for 2,000 years. And then in 40 days, basically, this AlphaGo, learning from scratch, rewrites the rules of Go and how to play the game of Go. Like the things it found, humans don't use yet in that context, like specific movement patterns. And so this also point at I think a very fruitful collaboration between humans and machines, where we can learn from what they're doing and what we're doing. And I think with that, I want to say thank you, and thank you for your attention.